Thank you, Tianzu, for the nice introduction and for this chance to show my research work. That actually this research work from my PhD work. So today I will talk about totally on experimental point of view. So my total background means the whole background after my say high school physics. So high school. So from metallurgical and materials engineering. And so I know you maybe in the audience group, so they may be from mechanical or the other department. So if anyone have any issue or say any question, okay, stop me anytime. Okay, we can discuss whether I will try to address your problem. So today my presentation topic is microstructure and mechanical properties relationship by controlling iron aluminum intermetallics and intermetallics of dissimilar electron beam welded different steel to aluminum alloy. Okay, so in this, say this name is too big, right? The title is too big. So now we can summarize or so we can sort it out. Say microstructure and mechanical properties. That means the performance of the joints. Okay, by controlling this iron aluminum intermetallics. That is means the main problem or issue because for this steel to aluminum alloy, and we did this welding by this electron beam welding process. So regarding the topic of the today's talk, so first I will start with the electron beam welding fundamentals. So its advantage for say similar and dissimilar combination, and what is the challenge if we do for say different steel to aluminum alloy welding, and then that challenges we will discuss in two case studies for optimizing the parameter in terms of or say controlling the intermetallics for getting the optimum condition for getting the actual or say the mechanical properties point of view. So the agenda of today's presentation I divided into 4 different groups or say parts. First, I will talk about myself and my present institute. It will take around 4 to 5 minutes. Then I will introduce electron beam welding system and with the help of say iron aluminum phase diagram. It takes around 10 minutes, and then I will discuss about the two case studies. First one is the Fe 7% aluminum alloy to mild steel and DP 600 steel to 5754 aluminum alloy. Individually, it will take within 15 minutes. So, regarding me, so I am currently associated with the National Institute of Technology, Rourkela, and joined as assistant professor in the Department of Metallurgical and Materials Engineering. And before I joined here, so my whole degree, as I say, from Metallurgical and Materials Engineering, starting from my graduation, that is a BE, Bachelor of Engineering, from Jadavpur University, then MTech, Master of Technology from IIT Kharagpur, and PhD from IIT Kharagpur in collaboration with WMG. Because my co-supervisor from WMG, I think you know all that Dr. Prakash Rangam is my co-supervisor of my PhD. So after finishing my PhD at the last of 2019, I think November end, so I moved to Toronto, Canada, joined as a postdoctoral fellow in the materials engineering department. So I stayed there for more than 3 years and came back India in the month of April end 2023 and joined here as a assistant professor at NIT Rourkela. So in terms of achievement, you can say that everybody knows that achievement means in terms of publishing papers. So I published more than 27 papers and attending multiple conferences like say TMS 2017-19, AIS Tech 2020, STIS 2022, and NMD. NMD is the Indian National Conferences, that is 2017, 16, 17, and 18. Currently, I am supervising 7 undergrad, 3 MTech, and 2 PhD students. And in terms of award, I got the MITEX Fellowship for carried out my postdoctoral research at University of Toronto, and some conference award, the best oral presentation, and I received the MHIT, that is the government fellowship for carried out my MTech and PhD work in India. So in terms of skill and expertise, I totally devoted in all say both experimental. Say experimental means the microstructure and the mechanical properties characterization, physical model and the CFD modeling using ANSYS. And last 2-3 years, I started using machine learning and in different metallurgical process for optimizing it. So now, in terms of my institute, so if I directly go to the website of our institute, yeah. So this NASA NIT Rourkela, the National Institute of Technology, is a government of India affiliated institute. So in this institute, we have total 20 engineering department, and our student is near about 6,500, and faculty is more than 420, and the staff of 350. So now, if you look into our department, so metallurgical and materials engineering, we have total 20 faculties right now, and two more will come within say 2 or 3 months. And we have say yearly our BTech strength is near about 1995, and MTech and then PhD. So if you want to check our website, then you will get the actual or say in details about our institute. Now, if I ask about the facilities are available in our institute, so this one is for say central research facility. We call it say CRF. So this facility is available for all 20 departments. So with the conventional characterization technique, we do also do have say ACM, EBHD, TEM, confocal microscopy, then secondary ion mass spectroscopy. These things are available as a central source. Means anytime we can book the slot and we can do the experiment. But if you see our departmental facility, so in our metallurgical engineering department, we do have a lot of experimental and the computational facility. That's in terms of microscope, that is a confocal, ACM, TEM, scanning probe microscopes are available. And some of these facilities I also in charge, or say other professors are in charge in that system. Suppose a computing facility, I'm the in charge because I'm working on say computational or say CFD part. So we have the ANSYS, MATLAB, Abacus subscription, and also we do also have HPC system. HPC means high performing computing system. And I do have two clusters having say very good configuration of 128 GB RAM with 10 terabytes hard drive. So because if you use ANSYS or say MATLAB, we need to high configure computer to do the simulation work quickly. In terms of mechanical test, we have say tensile for room temperature, high temperature, compression test, fatigue, micro harness. In terms of XRD, as a diffraction, we have say phase, texture, stress. Which these maximums are microstructural characterization techniques. Are all are means maximum say about 90 to 90%, 95% characterization technique or some machines are available in our department. But we are very short in welding equipment. So we have only TIG and MIG welding machine, that is the tungsten inert gas and metal inert gas welding. But we do have some welding machine in our mechanical engineer department. But for our department point of view, we have only TIG and MIG. So that's why, yeah, I contacted Professor Derek and Professor Pascal that okay, then we can collaboratively do some work. Say other characterization like say DSC, TGA, DTA, wire test, dilatometry, CHNS analyzer, or spectrometer. So let's move to the part 2. Part 2 is related to our electron beam welding. So suppose before going to electron beam welding, this graph is well known, and I think everybody know this graph. That is the heat input versus power density variation among all or say different welding processes. In comparison with gas welding and the arc welding process, the high energy beam density welding like laser beam welding and electron beam welding, the heat input is quite low, but the power density is very high. Power density is very high. So that means say in case of the heat input, the units say near say 10 to 100 watt, but in case of power density is 10 to the 5 to 10 to the power 7 watt per millimeter square, because the beam diameter is very small in micron in size. So this high energy beam density gives a very good penetration, very high welding speed we can achieve, and quality weld we can get. But in terms of say if we put heat input is quite high, then it will damage our workpiece in much more area. So, so suppose we have say two conditions. One is the homogeneous microstructure, and another one is the say distorted or say some damaged microstructure. Definitely, the homogeneous microstructure give you the most or say accurate mechanical property compared to our disturbed microstructure. So the low heat input with respect to the high power density is preferable for any type of welding or say any thermomechanical treatment. Now I try to get attention. So I know you maximum are from say laser welding guys. So I am trying to give some credit to myself. So comparison with laser and electron beam welding. So this is a simple schematic, or say this is a schematic of the laser beam welding process. Electron beam welding process. In electron beam welding, the whole operation we perform in vacuum atmosphere. So two types of vacuum are maintained. First one is the gun vacuum and second one is the wax chamber vacuum. So as we know that electron is the main responsible person, or say responsible item that helps to do the welding. So we have to create or generate electron. That we can create by creating the potential difference between say cathode and anode, and we can attract an electron to come to the work surface or so workpiece at very high velocity to do the melting and to the welding to take place. This some adjusting some coils to get the say concentrated beam on the workspace. And now we can imagine the it gives a work chamber vacuum and the gun vacuum level is 10 to the power minus 5 to 10 to the power minus 6 millibar. So in that high vacuum range, so there will be no atmosphere. So there will be no interaction or say reflection between electron and the and your say atmosphere. So there will be no diffraction. So we can get say the more high depth wedge ratio. That we will see in the next slide. That is the this is the means the fundamentals of electron beam welding that we already discussed. And now see the advantage. There is a with comparison to the other welding process. That is a high depth to weight ratio. A very high vacuum we are creating. That's it gives the quality weld. So low heat input and very high power density, narrow fusion zone and heat affected zone, because the distorted area will be very small and the beam diameter is very small in micron level, say at 300 to 500 micron. In this case, no need of filler material. Also, we no need to make any geometry, say group type of geometry, we no need to make. And ability to join, say, any type of material or say varying thermal conductivity, melting point, any type of material we can do. Suppose for in our case, we are doing welding of steel and aluminum. And think about the melting point difference between, say, for aluminum, say 600 or 660 degrees Celsius, and the steel is near about 1500 or 600 degrees Celsius. So it's a huge difference in melting point. So that thing also we can do weld by this electron beam welding process. So this is the advantage, say rather from your laser welding, but laser welding also have some key points that you guys also know better than me. But what I assume that both laser welding and electron welding principle is quite similar. Only vacuum atmosphere is applicable for the electron beam welding process. And one more important point or drawback is the small workpiece. So suppose so in our welding machine, say is a academic institute, so we have the welding machine, electron beam welding machine, having say movement of your say, material at the welding chamber. That's a 200 millimeter in X direction, 200 millimeter in Y direction. So you can imagine that how small it is. Means only 200 by 200 millimeter we can weld. But we have say DAE lab, Department of Atomic Energy of Government of India. They have the one electron beam welding machine that the vacuum chamber is so big that four to five people can go inside, fix the material, and come outside. Then make the vacuum and then they do the welding. So they try to solve this size issue, and definitely this is a high cooling rate. For electron beam welding, definitely it is a problem because high cooling rate may sometimes create a different type of crack. Now, so with the conventional welding processing conditions, suppose voltage, current, welding speed, we add one more welding condition, that is the beam oscillation. And beam oscillation is the deflection of electron beam from the straight line path to give any periodic motion. And there are possible different oscillating patterns, say sinusoidal, square, triangular, ramp, circular, elliptical. There are different circular patterns we can give. But the literature suggests that there is a negligible effect of different type of pattern. So we choose the simplest one or the easy one, that is a circular oscillating pattern in our case study. So from the literature, we found that if we use the beam oscillation, we will get this type of advanced property or say in addition property compared to our without oscillation condition. Suppose a more uniform and smooth microstructure, it is reduced porosity and other defects, and this point. So for our study, we will justify each and every point whether this all the points is matching or not. Now, our material combination is different steel to aluminum alloy welding. And we know that this combination is widely used in different aerospace and the automotive sector. Here is the example of two aerospace industry, that is a Boeing 787 and say Airbus 380. So we can see that near also 40 to 50% steel is being replaced, different grade of steel is being replaced by the different grade of aluminum. And in automotive sector, like the example of say Mercedes, Audi, Porsche, Volkswagen, so everywhere we say that the 40 to 45% aluminum is used to reduce the weight of your body, so that it will increase the fuel efficiency and reduce the carbon dioxide gas emission. And by virtue, all this steel replacement by the replacement with aluminum is only possible by the welding process. I'm not saying that it's only possible by the electron beam welding process, by different types of welding process. So welding is the key solution for the replacement of the steel partially with different type of grades of aluminum. So now the main problem associated with this aluminum to steel welding is a phase diagram, because it's a phase diagram of iron and aluminum, and it's not quite straightforward phase diagram, just like say copper nickel or copper zinc phase diagram. There's a complete solid solubility making the binary phase diagram. It's a very complex phase diagram. So now we can see that in x-axis, so aluminum, say steel, iron, and aluminum. Now we can see that nearly 10 to 11% aluminum is soluble in iron matrix. So if our aluminum addition in steel is less than 10 to 11%, that means that will give you the solid solution, give the accurate or say more mechanical properties. But if we add more, then what will happen? Then there will be chances for different types of compounds formation. Now we can summarize what are the different types of compounds that form in case of steel to aluminum welding. And these compounds are called the intermetallics. And these are different types: FeAl, FeAl2, Fe3Al, Al6, different types of intermetallics are formed. So, and this formation is only possible or so only happen because a change of weight percentage of aluminum and the different level of temperature of application or different experimental condition. Now let's move to our first alloy system, that is Fe 7% aluminum alloy to mild steel. That is quite more almost similar type of material, but this Fe 7% aluminum we got from Tata Steel Netherlands, and this Fe 7% aluminum alloy is gaining interest as a replacement of steel because of the lightweight nature, because of 7% addition of aluminum. So as it contains less than 10 to 11% aluminum, so it will be easier to weld, and we can say overcome or say we can restrict the intermetallic formation. So in terms of say experimental condition, so this is the chemical composition of the both material. That is the FeAl alloy is aluminum percentage is near about 7%, and this is the normal mild steel having the carbon percentage maximum 3%. And this is our processing condition. So now if we try to divide this processing condition in three different ways, say constant parameter, varying parameter, and the calculated values. So constant parameter, that is the beam voltage and beam currents, where we keep it fixed for every condition. Okay, but varying beam parameter is the welding speed and the beam oscillation. The good thing is that now if we compare between joint 1 and joint 2, that means welding speed is fixed. Okay, but in case of joint 2, we are using oscillating beam as a 1 millimeter dia as a 600 hertz frequency. Now if we compare joint 1 and joint 3, now we can see that we changing the welding speed, but in both cases we did not use the beam oscillation. And we calculate the heat input, and heat input calculated by the V into I, that is the voltage into current by the welding speed, and we can see the heat input is quite low, 0.061 kilojoule per millimeter. And the weld width that we calculated after taking out the sample from the chamber. So now, in my opinion, if you want to make any welding or after doing the welding, first criteria or first observation should be your defect characterization before going to any mechanical or say metallurgical study. And for defect characterization, we first select the X-ray tomography. And this machine, I think all of you very well know this machine. This is from WMG. Okay, and the working principle of this XCT or tomography is that. So this the middle portion, this one is the our sample or object, and we put the sample in between the X-ray source and the skin, that is called the detector, and this sample we put at the rotating table so that the sample can rotate in 360 degree. So when X-ray, we start X-ray, it go through the material, then this depending on the material condition, it may be attenuated or maybe go through within the material and make create the image background at the projector scale. Okay. So now if what we will do, that is a similar type of say our X-ray. Like if you want to go say any health clinic, then if you want to make X-ray of our hands, say it's broke my bones, then they do the same thing. And then this is the 2D, right? So after making the say one single say angle, then we can rotate the table in 360 degree rotation so that we can get the projection of the image in the 360 angle. So then by the 3D object reconstructed by the backpropagation method, we get this 3D volume of our scan image. And so, as you know, in 2D means we have only X and Y direction. If we want to make 3D, that means we need the Z direction. And that Z direction we have to make by the slice of the, just a cake slice. Now, so before going to say X-ray tomography, we first did the X-ray radiography. For doing the same machine, okay, we scan the whole sample. And we can see that it's visible, say, wormhole or say lack of fusion type defects found in case of joint 1 and the joint 3 respectively. Or the wormhole is just like say agglomerated pores or say accumulated pores. It's accumulated in one place. And lack of fusion means the lack of penetration. That may be due to the say high welding speed or the any other welding condition. It's not appropriate welding condition. So then we did some image analysis. That image analysis is performed by the image software. Okay, and then we did some background subtraction, filtered image, and thresholding, everything we did. And after segmenting the image, we get some result. And this is the quantified result. But what everybody should understand or know that this image analysis later is not good for quantitative data. But this experiment or this study we can perform to get the trend of our result. We are not talking about the individual parameters, say 7.5 or 267 or 269. But we can get 10 from say joint 1 to joint 2 by using the oscillating beam. We can see that the numbers are decreasing. If big size are decreasing. But we are not asking about the individual number. But in case of joint 1 to joint 3, we can see the numbers are increasing, but the maximum bigger size are decreasing. So we can get 10 before going to the 3D tomography result. So we know that the joint 2, by using the oscillating beam, we are getting slightly or superior result or superior property in terms of defects. Now we did the tomography result, and this is the 3D tomography images. Okay, so and this sample is 1 millimeter by 1 millimeter base, and is a height of say 5 millimeter, and the top portion is the Fe7% aluminum alloy, and the bottom portion is the Maya steel, and this green color is the pores. And now, if you for closely look or say for proper visualization, we take the orthogonal slice, and we can see the pores. Now, if you see the ports is very size difference is very different, and the shape also different. Now, if you try to look the individual ports, the biggest size one. So this is the biggest port. Okay. So in case of joint 1, we see the circular or spherical. Joint 2 and joint 3 is the irregular shape of pores. And we know in case of welding or any thermomechanical treatment where melting is involved, there will be two different reasons for the porosity formation. First one is the gas entrapment or gas involvement, and second one is the contraction pore from liquid to solid transformation. And we know that gas entrapment pores spherical in nature because of the lower surface energy or surface energy interfacial energy of the gas. And that we can also justify with the help of sphericity calculation. That means sphericity, if sphericity close to 1, that means x and y direction is close to 1, that means perfectly spherical. And we find out that in case of joint 1, the sphericity close to 1 is maximum, but in case of joint 3, the sphericity is far away from the unity. So that means the gaseous pore formation trend that will be more in case of joint 1. And now if you try to look, say, what will be the reason for gaseous pore formation, or which type of gas is involved for the gaseous pore formation. And so that we did the Raman spectroscopy study. So with the say advanced Raman study, so yeah, I'm not expert in Raman study, but what I know that so the X-ray source, laser source will be go through with your material throughout the thickness, and if is there any discontinuity, then it will show the shift or say peak. That is called the Raman shift. And from the literature, we found the hydrogen is responsible for the gaseous pore formation. Then question will come, why, from where this hydrogen gas comes? Because we are doing welding at a very high vacuum. This hydrogen may come say within the material during casting process. Otherwise, maybe when we are mechanically putting the material together before putting the material into our vacuum system, there is some gas pocket or air pocket may be enter within this. So, and we found only hydrogen gas is there or responsible for the gaseous pore formation. And then we do the quantitative study. First, see the effect of beam oscillation. If we compare between joint 1 and joint 2, we see the beam oscillation effect. And we can see that in case of joint 2, we did not find any bigger size pore. That means pores are very small in range. But in case of welding speed, if you increase the welding speed, that means joint 1 and joint 3, here also we can see the bigger size pore is invisible, or say it's not there in case of high welding speed. Suppose say more than 30, it's not visible, only the black, that is the joint 1. So, so from the porosity or the defect point of view, we can say that joint 2 is the say topmost position, then joint 3, and then joint 1. And then we move to the mechanical properties. So we have the defect background. Then we do the mechanical property. Mechanical property means we did the micro harness. That is, in case of micro harness, we just see the harness difference of the both HZ region because of the grain size change from the weld zone to the base metal side. Okay, that's why your harness is changing. But in other cases, we see the similar type of trade of the harness for the all three conditions. But if you see the tensile stress, that means if we go for the tensile study, now you can see that we have to put two different graphs because they see the scale. For FELI base metal, the yield stress is near say 900, and but in case of say steel base metal MST, MS, or say other three joints, this is near about 4 to 450. So that's why they are looking for this alloy, FELI alloy. But see the strain. Strain means the elongation. Elongation is very less. There is only 2.5, where is near about 12%. This is the contrast or property. Right? Now, if you try to compare with all three joint conditions, joint 1, 2, and 3, we can see that YS, that is the yield stress, and the UTS, that is the tensile stress, or the ultimate tensile stress, is not changing that much. It's quite similar. But check the elongation. In case of joint 2, we got the elongation near about 13%. Compared to your 9%, so 9.6, joint 1, or say joint 3 is 2.8, is the lowest one. So in case of joint 2, we are getting the elongation maximum is very close, or say is very close to our steel base metal. And see this where these samples are break. There's not even in HZ, not even in fusion region. Now, if you see the image of this tensile broken sample, you see. This is my say the whole gauge length, and this is my fusion area. This is my fusion area, and sample is break far away from the fusion zone. That means our weld joint is strong enough, or more stronger than our base metal. And then we did the factograph study, that is the ACM factograph, to know which type of fracture surface is coming. And in case of joint 3, we saw that this is a ductile mode of fracture. But in case of joint 1 and joint 2, we found that is a cope type of fracture, or say dimple type of fracture, that is the ductile mode of fracture. And then we go for the impact study, the impact load, that is the Charpy impact study. And for that, we see that in case of joint 2, we get the impact energy maximum compared to your joint 1 and the minimum for the joint 3. And then again, we did the factograph study. So in case of joint 3, so joint 1 and joint 2 shows the say dimple type of fracture. Okay, and but in case of joint 3, that is we saw the quasi cleavage, that means towards the brittle mode of fracture. And most interestingly, we did one more thing, that is the X-ray tomography for the whole sample, for one side, definitely one side. We are taking say Fe 7% aluminum alloy side to see the how the cracks looks like. So in case of joint 2, we see the very small size cracks, and but in case joint 1 or say joint 3, we see say the cracks are very big that are connected, interconnected to each other. That's why they see the color coding. That's why we got the very big size cracks. So we know the mechanical property or the performance of the joint. So to discuss about the effect of say, mechanical properties of performance, we need to study the microstructure. So if you try to look at the microstructures, that is say first is the for joint 1, this left side one, this is FEL alloy, and right side one, that is the plain carbon steel, and this is the fusion zone area. And in both cases, we have the two major alloying elements, that is the aluminum and carbon. So now if you see, compare with these three condition, three welding conditions, joint 1, 2, and 3, we can see that this in case of joint 3, there is very minimum distribution of the carbon or aluminum both in the fusion region. Whereas this distribution is more and more uniform in case of joint 2 and a little bit good about say joint 1. So that's why this iron and carbon and aluminum, this is the major alloying element in both cases. So that is the reason for getting the worst mechanical property, because of the poor distribution of the alloying element throughout the fusion region for the joint 3. And then we go for the say textural study for using say ACM for EBSD. So that EBSD texture, that is called the micro texture, because the ACM beam can penetrate up to say 10 to 20 micron of the depth from the surface, and this textural study is the study of the say 10 to 15 20 micron. And so this is FELL side, and this is the mild steel. Okay, and this is the last one. This is the inverse pole figure of the showing the 001, 101, and 111. So this color coding will help us to understand which type of grains are oriented along which direction. Okay, so both mild steel and FELL both are BCC in nature. So, and we can see that in case of joint 1, so three types of both gates are we can find all three gates are oriented in three directions. We will be see for different gates, but majority of the gates for joint 1 is oriented along say direction 101 and the 001 direction parallel to India. It means normal direction. In the joint 2, we get the 111 and the 101. So in case of BCC microstructure or crystal, so if our grains are oriented along 111 or say 101 direction more, then it will give more mechanical property before going to fracture. So we know the microstructure, microtexture, and then but for say suppose our say welding material say thickness is 4 to 5 millimeter or say 10 millimeter, but so this microtexture will not replicate our total mechanical properties which we are getting. So for that we did the neutron deflection study for the bulk texture. So for this study, our material thickness is 5 millimeter. So we can see that the neutron beam is 5 into 15, and the neutron wavelength we use 0.2 to 3.5 angstrom. And this experiment we perform in RAL, Rutherford Appleton Laboratory in UK. And for this test macro texture, we discuss with the help of ODF, that is the orientation distribution function. This also we can discuss with the help of say IP inverse pole figure or pole figure also. But ODF distribution is the give you the complete idea which type of texture or so which type of deformation or fiber deformation we are getting for different conditions. The first left hand side, that is for the base metal, and the lower left hand side, that is for the HJ, both HJ, and the right hand side, this is for the fusion zone. For top portion is the FELL and bottom portion is the steel. And this structure, or say this one, you will be determining to understand which type of fiber components are present in which position. And for the BCC, because both are BCC in nature, so here phi 1 should be 0 to 90, and phi will be 0 to 90, at phi 2 at 45 degree. So, and this is the double bracket is the plate, and this is angle, right? So one on plane at one on zero direction, similar like this, and we can find which type of fiber component is present in which cases if you see this type of with this ODF. And we know that the gamma fiber promotes the deformation, and the gauge fiber promotes both the recrystallization and the deformation. But in case of BCC, we have generally four type of fiber components are there. That is the gamma, gauge, rotated gauge, and alpha. So if we try to correlate this figure with the means right hand both at the top and bottom figure, we can see that in case of joint 2, these two, okay, for BC both the FEL, alloy, and the steel, we are getting say gamma and gauge fiber compared to our joint 1 and joint 3. And this gamma and gauge fiber attributed for better heat mixing and reduce the unidirectional solidification gradient. What does it mean, unidirectional solidification gradient? That means, suppose we have say two types of microstructure having say directional solidification, because say in case of our welding, we preferably do the directional solidification by putting say certain welding speed, and so that will give you the directional or say directional solidification gradient of the grain. But in other cases, if our say unidirectional solidification takes place, just like say casting, that microstructure is more homogeneous compared to your directional solidification. So then the question will come, what is happening if you use oscillating beam or say beam oscillation, that will change the grain geometry, gain morphology, gain direction, everything. That we can discuss with the help of these things that that is proposed by this authors 2016. That if you say this is for the left hand side, that one that is for say without oscillating beam, that means the normal beam. And with the specific beam diameter, so when beam moves in a forward direction, that beams will be from weld bead, also weld bead will form as a overlapping of a small weld bead. And as we know that the liquid and solid both phases are there, so Marangoni flow will act strongly. And for the most of the material, Marangoni flow direction will be act as a outward to the outward direction. And this when we move forward, our torch or say electric torch or say laser torch, and then our solidification will take place towards the front direction. But if we use say oscillating beam, say this is my beam oscillation, this one. This is my beam oscillation, and so for when say for the same length, our beam is move say travel longer distance. So individually it will form a small tiny weld pool. And now we can see that there will also be some overlapping will be there. But when this beam will move to this side, again it will melt again. That means repeated melting. Repeated melting will take place. So that will give you the churning action, and also repeated melting and solidification will dictate the overall cooling rate, so that our microstructure will be changed by the use of oscillating beam. So now let's move to the part 4. That is the second set of material, that is DP600 steel to 5754 aluminum alloy. And now same say this is the chemical composition of our material, where the DP steel means the microstructure is ferrite and martensite. That is the martensite will be the infrared matrix. And if that is the 5754 aluminum is the say pancake type of microstructure we are getting, where the major aluminum element is, because this is the 5000 series, so major aluminum element is magnesium. And in terms of process parameter, again what we did, now we divide say 3 parameters, that is the constant beam parameter, varying beam parameter, and the calculated value. Now from the previous set of example, we came to know that okay, oscillating beam gives the superior property compared to your welding speed or the non-oscillating beam. Now what we do, we remove the higher welding speed condition. Now what we did, we changed the oscillating diameter from 1 mm to 2 mm. And from the literature, we found that oscillation frequency have a minimum or say negligible effect. If we change from the 300 to 600, then that difference does not change the mechanical or microstructural property that much. But this parameter, this guy say 1 millimeter to 2 millimeter, the beam diameter play important role for microstructure also mechanical properties. So, and here also we change in beam current or increase beam current little bit, but very negligible, within 2% or say 1%, to get say proper say 100% penetration, say full penetration to take place. And see again we calculate the heat input. So here if we compare between amongst the joint 1, 2, 3, the joint 1, is without oscillation, joint 2 is the 1 millimeter oscillation diameter, joint 3 is the 2 millimeter oscillation diameter. Now let's see similarly we did the porosity defects. Again we find out the top portion is the DP steel and the bottom portion is the aluminum alloy. So we found that the porosity is formed, and we see that the aluminum alloy side is porosity formed extensively compared to your steel joint. This is because when we are doing welding for this set of material, we did not pass our electron beam at the junction point. We offset the beam towards aluminum side of 1.5 millimeter to melt the aluminum and to restrict the steel melting, so that we can restrict the intermetallics formation. And we did by say some literature study, some experience, and some trial and error method. And this is the individual port geometry. That is again we saw that there's spherical ports and joint 2 and joint 3 showing the irregular shape port. And now, very interestingly, again we did the Raman spectroscopy for the gas analysis. But this case we did not find only hydrogen. We also find oxygen and nitrogen. And we found the peak for all three cases. So we can say that for the gas identification of the gas porosity formation is controlled by all three gases. But because of the three gases, then what we did quantify of these gases. So in case the total gas present is the maximum for the joint 1, that is the 343 ppm level, and joint 2 and the joint 3, it is the lowest one, 122, around 122 ppm. That means if we also use the oscillating beam, that means we are releasing the gas more. This is because check the fundamentals. Just remember the last slide I discussed that repeated melting and solidification and the churning action try to give say wider window for the material, the liquid material, so that the gas will be going out or so moving out from the liquid metal region. So then we try to find out say any other defects, and we found did first say room temperature XRD study. And here this is copper is a target material. There's a wavelength of 1.56 angstrom, and we find out that only very big iron and aluminum peaks we found. But when we tried indexing it, we found different intermetallic peaks, and these intermetallic peaks are 4 types: Fe4Al13, Fe6, Fel, and Fe3Al. And this peak, but we did not observe any individual peaks, the small peaks, because these base metal peaks are so strong compared to our intermetallic peaks. But we did the readable analysis for getting the quantified data, and we are getting the total intermetallics for is first decreasing for joint 2 and again increase. And what are the different types? This is the four different types of intermetallics: Fe3Al, Fe4Al13, Fel, and Fel6. And we are getting individual the amount of say percentage of intermediates formed for different welding condition or different joints. But this room temperature exactly does not give us a proper peak or so showing any individual peak. For that, what we did synchrotron diffraction study. So in case of normal XRD, the target material, the wavelength is 1.54 angstrom. But in case of synchrotron diffraction, the wavelength is 0.7843 angstrom. And this is a synchrotron graph. And here we only saw this iron and aluminum peaks. But at the small portion here, you see some small peaks are there. And then what we did, we scan the sample in the small 2 theta region, that is 19.5 to 22.5, and we got the intermetallic peaks individually. Okay, and then again we did say readable study, and we find out that the same 4 types of intermetallics are found, but the percentage value is a little bit different. So in previous cases, you can say 8, 5, and 13. Here we got 10, 7, and 14. So it's close, but what we assume for this synchrotron diffraction, because we are scanning a very small region, it will give more accurate result with showing the individual intermetallic peaks. So here we found both the porosity and intermetallic defect in case of our DP600 to 5754 aluminum alloy joint. And then what we did, then we go for the visualization of intermetallics, just like say porosity. And so with same sample, we did the tomography study for the porosity defects, for the intermetallic defects. And where we see again same thing, that means the intermetallics are formed but there are different ranges. You can see the scale of the volume in micron millimeter cube, and see the quantitative result. And now we see the total scan area. What is the percentage value of the intermetallics form? So for the joint 1, it's showing 0.24%, but in case of joint 2, it's 0.13. That means by oscillating beam, it goes to half. But in case of, if you increase the oscillation being from 1 millimeter to 2 millimeter, it goes to double, to 0.24 to 0.48. So it does not mean that if you use the oscillating beam, that means we are getting, say, superior property. That means we have to optimize the beam diameter also. So let's do by, say, ACM study. So now if you say for individually try to explain the graph. First one is you can see my mouse, okay, right? So this one for joint 1, the left hand side is aluminum alloy and the right hand side is a DP steel. So we zoom it for this region to do the line scan of the individual, say, iron and aluminum, the major alloying element, and then this is the area scan of the individual alloying element, and then in the small portion we try to do or say calculate the intermetallic thickness, and we can see the gradient of the iron and aluminum elements. Now similarly we did for the joint 2 and joint 3. Now if you see compare, say, this one and this one, check the slope. This slope is maximum for the joint 3, and also we can see the thickness. Right now, from the joint 1 to joint 3, 2, intermetallic layer thickness is decreased from 2.11 to 1.65 micron, and it's again increased to 1.77. That means in case of joint 3, instead of getting superior property, we are getting bad property in terms of defect point of view. Then we did TM for the intermetallic visualization, that is the transmission electron microscopy. So this is the individual compounds we found. So these 4 compounds, Fe4Al13, Fe6, Fe3Al, and FeAl, these 4 compounds we found in every condition. In every condition, joint 1, joint 2, and joint 3. How can we identify this particle? So first we can calculate this length or size, okay? And this is the SAD, that is the selected area diffraction pattern. So if you say this is my point, and the nearest point is 001 bar, and the second nearest is 200, and the angle between these two is 1.08. And from the literature or from the literature, we can find out this is for this type of compound, that is Fe4Al13. And also we did the EDAX of this particular, when we put the EDAX detector on this particular object or particular particle to get the EDAX study. So similarly we did for all cases, and we found out that all 4 compounds, that's Fe4Al13, Fe6, Fe3Al, and FeAl, all are found in all cases. But the interesting thing is for joint 3. In case of joint 3, we got some bigger size, some irregular. Suppose this is the needle type of shape, and see the unit, 1 micron. This is more than 4 micron, and this is in nanometer. So this is the needle shape, hexagonal shape. Also, we can see the cluster or the garland type of intermetallic form in case of joint 3. And we did the EDAX study and the SAD pattern study, and we find out this type of intermetallics are Fe4Al13 type of intermetallics. So, and our literature suggests that aluminum bearing intermetallics are more brittle compared to our iron bearing intermetallics. Just like, say, this one, this is the aluminum bearing intermetallics. That is the reason where we are getting very poor mechanical property, or say poor property for this joint 3. Now, let's say for any joint performance mainly depend upon first, say, defect studies, that is the porosity and intermediates. And the second thing is the residual stress distribution. Residual stress also one type of defects is formed due to the thermomechanical treatment or welding. And this is the typical graph we got. Say tensile stress at the fusion zone, and in both HZ we got the compressive stress because it's the negative value. Right? So now, if our tensile stress is more, that means that tensile stress is less, that means good. Or say residual stress, compressive stress is more, that is the good one. Right? And this is the parameter. Suppose that we did took the 2 theta peak at the highest strong peak, that is a 137.7 degree, and we did the expert high score analysis, and then find out this joint 2 showing that the tensile property is the minimum, is the red one, and but this the compressive stress is maximum. So this is more favorable in case of joint 2. So why this type of curve form in welding for the resource stress distribution? That we can discuss with the help of this diagram. So in the left hand side, this is the diagram, means the your heat source movement or moving, and then next this is the temperature distribution. Next one is the stress distribution. Okay. Suppose our point is A point, this point, where there is no heat source, there will be no heat input phenomena is happened, so no stress generation will take place. This is a normal condition. Okay, without doing anything. Suppose we are try to heat the material, or say our welding torch or laser torch is started at the say BB condition, B condition, this way. So stress goes to 0 at the below the heat source here, because when we try to melt the material, if our material is melted, there will be no stress, there will be no heat. The heat source is stress due to the expansion of this thing. But if the oil pool is liquid enough, there will be any strength to support the load. So that is the case. But if we remove this one, say away from the heat source, the negative stress is developed due to the expansions of this area, because we are transforming solid to liquid transformation, then the material will be expanded, and this negative source is restricted by the surrounding material, which are in the lower temperature. This is the condition, and then because our heat source is at that condition, so peak temperature will be maximum. But what will be the stress value? Stress value will be so the closest one will be the negative one, and that will be controlled or say balanced by the positive source, the surrounding material, that is the lower temperature compared to our this the adjacent to the welding region. Suppose our condition is C, this condition, where we are just crossing our heat source, crossing that point. Then our peak temperature will decrease, and what will happen? The weld metal, the welding material or welding portion at the adjacent base material have going for a cooling, and hence the cooling, then contraction will take place, liquid to solidification, thus producing a tensile stress, and nearby this tensile stress and where this tensile stress will be accommodated by the adjacent compressive stress will generate. At the means when our finish our welding, then there will be no temperature difference, but our restored stress graph looks like this. So this type of graph we also got from our study. Now let's move to the mechanical property. So mechanical property in terms of tensile stress. Okay, now we can see that this purely brittle type of tensile curve we got, where this curve looks like say ductile mode of curve, right? So in direct means falling or say the breaking is taking place instantaneously. There is not giving enough time for elongation to take place. Now let's see this yield stress. See the base metal yield stress 148, 358, but the yield stress is quite very low, near about 50 MPa. But it's very close. UT is also very close. But if you use oscillating beam for the joint to 1 mm oscillation diameter, we found the elongation is double compared to your without oscillation condition, that is 2.79 to 4.82. But in the joint 2, joint 3, it's again decreasing. And check the failure location. All joints are failed at the fusion region. Not like the previous condition, the joints are failure at the say out of the gauge length area. And this is because of the formation of intermetallics. So we did the factography study, and we calculate the dimple size. As you know, that if our dimple size is average dimple size is big enough, that's the biggest one. That means the chances of ductile mode fracture will be more. But in case of joint 3, we are getting the lowest dimple size is 2275 nanometer, and the highest for the joint 2. So that's why joint 2 giving the maximum elongation percentage before going to the fracture. Then we did the impact study. The impact study we did for by the use of Chappie impact study. Again, we get a similar type of time that joint 2 getting the best or say maximum energy. And we did the factograph analysis again and calculate the dimple size, and did again the tomography study for to observe the crack nature, that is the crack or form due to the study of the Charpy impact experiment. And then we did the micro hardness, and it's clearly visible of the formation of intermediates of sudden increase of the hardness value in both HZ region, HZ or say base metal to weld region, and the formation of intermetallics compound. Now we did the microtexture by EBHD, and we know that aluminum is FCC in nature, and so in case of FCC crystal structure, there are 5 types of fiber components are formed: cube, copper, brass, ace, and gross. But all these different fiber components is used or say controlled by the different things. So the cube texture, cube fiber component is controlling the recrystallization texture, whereas the copper, brass, and ace is the deformation texture, and gross both contribute in both ways. But from our result, we see that the major components also for joint 2, we are saying the major gates are oriented 111, 112, and 634 direction. That is for the deformation texture. That means, so before going to fracture, we will getting the maximum mechanical property in case of joint 2. So what is happening then in case of joint 2 and joint 3? Because both cases are oscillating beam, right? So, but this is 1 millimeter and third one is a 2 millimeter. So when we are increasing the oscillation diameter, there may be chance that it exceed the limiting overlapping factor or limiting overlapping area by increasing the oscillating diameter. That may be from 1 to, if we choose say 1.5 or 1.75 millimeter diameter, then maybe we are getting more say superior property, but 2 millimeter is the that exceeding the limiting factor or the limiting value of the overlapping. That is the reason for why in case of joint 3 we are getting the worse mechanical property or say very high in welding defects compared to your joint 1 or say joint 2. And we also did calculated it for this, means what is happening in terms of actual heat input. And that is calculated by is back radius and the normal radius when we are moving or so rotating our welding beam with beam oscillation condition. And this is the point. What will be the point? Point 2 is the say repeated melting and solidification. That will give you say more enough time for gas to escape from our material. And third point may be the churning action phenomena. The churning action of weld mold during beam oscillation leads to the more homogenization or say reduce the elemental segregation or say supersaturation or say intermetallics formation. But if intermetallics form, how it grows? I missed one slide. So that intermetallics formation, how it grows, that is grown by the RNAS type of equation, right? So if we increase the temperature, that means according to the RNAS type of equation, your intermetallics thickness will be increasing. But by using the oscillating beam, we are decreasing the peak temperature, decreasing the cooling rate. That means we are decreasing the intermetallics growth phenomena. So that's why we are getting smaller type of intermetallics or say very less in quantity in case of optimized condition. So this is the conclusion. So conclusion in say 1 or 2 sentences will be that say oscillating beam or say beam oscillation at optimum condition will give you the superior property or say superior mechanical property, and that can be discussed with the help of say defect study and microstructural study by controlling the intermetallics. But if we go beyond our optimum condition, we will get the inferior property. Regarding right now, because I have recently joined, so just last 1 year I joined. So I am doing some research work with some professor. One is from University of Tokyo that we submitted one proposal on AIML on BOEP, that is a basic oxygen furnace. That is the prediction study that Hiroyuki Matsura, and with Professor Derek and Professor Pascal. So we already signed CTT proposal and MOU is in progress. And also we submitted one proposal to Indian government, that is the ACRB SAR proposal, so that I can visit WMG for 5 to 6 months to do some research or to start collaborating the work. And these 2 guys from University of Toronto, my postdoc guides and my mentor. So right now also I am also working with this guy. And these things are doing the modeling part, that's the metallurgical process modeling using ANSYS. And this is this is my group here. There's a young group in my institute. So it consists of say BTech, MTech, PhD all. And thank you for listening. Thank you for the patience.
Yeah, thank you very much for the very fruitful intro, presentation. We slightly run over the time, but I think it would be good if, anyone can give the questions or any comments you have. So, and also, I mean, there's the email, I mean, shared within the contact address shared within the email. So if you have more questions, you can also follow up later on after the presentation.
Yeah,
So
then anytime. If anyone have any query or any discussion, okay, just drop a mail, then we will discuss.
yeah, so any questions at this moment?
Hello, I have a question.
Yes.
Thank you for your presentation, Sumitra. I'm Ali from WMG. I'm also working on laser welding of steel to aluminum. I just have a question. Checking your publications, I realized that most of the work you have done is on butt welding configuration. I wanted to ask if you have any work on overlap configuration.
No, for my study, for say, in terms of say my PhD work, okay, I focused on say part welding. So, but regarding our say joint preparation during say DPC 600 steel to 5754 aluminum alloy, so it's very tough to do welding this dissimilar condition. So I tried with say part welding, lap joint, and say dissimilar thickness. Okay, so I put say steel thickness is 2 millimeter, aluminum is say 4 millimeter. So I tried in different cases, and also during that time I did the lap joint also, and I also succeed with the joints. Only 2 or 3 condition I did, yeah, but that is not included in my PhD work as
Okay.
per the plan from my supervisor.
The thing is, I realized that in butt welding also almost always you apply the beam toward aluminum side.
Yes.
Do you have any experience with applying the beam in
Steel
steel
side,
side?
right? Yeah, I know.
And what's the
This question will
reason?
come.
Yeah, what's the reason for going toward aluminum side?
Yeah, because and trust me, when I was looking for the reference journals. Okay, so maximum papers, so I found say they are shifting the beam towards the steel side.
True.
So because yeah, I don't know means why they are doing this, but they are trying to say justify their comments why they are shifting the beam towards a steel side. But what I did, my concept is that I shifted the beam towards the aluminum side. Say for our cases, I shifted to 1.5 millimeter. This is because of 2 reasons. First one is the say aluminum melting. Okay, now if I try to say do say steel melting, say at say 1600, 1800 degrees Celsius, so a lot of aluminum will be vaporized. Okay, I'm not saying the aluminum will melt simultaneously, but that effect will come. But one more thing, I did aluminum side melting to restrict the iron melting to control the intermetallics, but we need diffusion to take place. Otherwise, no welding will be done, right? So what I did, I shifted the beam towards aluminum side, but before putting the welding torch towards aluminum side, I preheat the steel side just a 0.5 millimeter say away from your wall, okay, to preheat say 2 or 3 times so that it's preheated say a little bit, so heated, then diffusion should take place. That is actually my objective, also my work that time.
Good idea, yeah. So just out of curiosity, did you compare the results with beam applied to steel and beam applied to aluminum side? Is there any comparison?
No, steel side actually I did not perform that time.
Okay. Okay, thank you very much.
Yeah, thank you.
Any other questions? Okay, I think maybe if there's any questions, we will reach you by email maybe. And before ending this meeting, I think I have one question. So in your presentation, the circular beam oscillation pattern was introduced. Have you tried other types of oscillation pattern like the zigzag and the figure 8, and like the transverse oscillation in the shape of the sine and the cosine shape?
No, actually, so I did not perform that experiment, but my say my senior, okay, from my batch, okay, so means that time he was doing PhD, so he did play with the pattern type, okay. So, but he did say sinusoidal type, and the circular type, and the zigzag type. So he tried with the 3 different types, but what he concluded that the type of oscillating does not have that much of effect on say properties point of view. But and also one more thing, that is the frequency. He also tried with the frequency also, means changing frequency of say oscillation pattern, say 300 hertz to 600 hertz. And he also concluded that frequency does not have that much of variation, or say does not change the property of the joint. So that's why I removed that 2 condition. I play with the oscillating diameter.
Okay, yeah, thank you. I think there's one more question from Koma. Yeah, go ahead, please.
Hi, thank you so very much for such a nice presentation, and it's a lot of experimental work. And I just have one quick question about selective IMC formation. So you showed there are a bunch of the IMC may form, so we can't like avoid them. But is there any way to do like something with the beam shaping or beam oscillation for some of the selective IMC formation, you know?
Yeah, so yeah, I know, I know a little bit about beam shaping, because you guys are working on beam shaping. So and so Anand gave one presentation in our international conference last year. So in that presentation, he talked about the beam shaping. So that's why means I don't know about the beam shaping. Can we control or not? But in case of beam oscillation, so we can play with say suppose which type of intermetallics will form at what region, that will be controlled by say, if we see the iron aluminum phase diagram, that will control by the temperature and also the composition. Okay, so composition we cannot control during the experiment, but what we control, we can control the temperature of formation. Suppose so from the theory or say from the literature, we know that aluminum bearing intermetallics are more brittle compared to your steel iron bearing intermetallics. So we can play with the say beam oscillation parameter, beam oscillation diameter, okay, or say beam oscillation diameter, say slightly we can change it, or maybe we change the oscillation shape. That's what Tianzu says. Maybe we can use other type of beam oscillation pattern, so that we can restrict, or we can say intentionally give some temperature region, or say the calculation temperature, say actual temperature during the welding, so that say preferable intermetallics will form that time, rather than if you try to say separate, say we don't want aluminum bearing intermetallics. Intermetallics will form, IMC will form, but we want say iron bearing intermetallics to form. That we need to carry out say some experiment having with more operational window. That means we need the parameter, right? We need to change the parameter so that we can play with the parameter to control the intermetallics in different types. Then maybe we can try. But what I understand that this is intermetallics will form that we cannot control, but we can control the types if we play with the other parameters. Means beam oscillation definitely one parameter. Maybe we think about say beam shaping also maybe another parameter. Then we can try with that. Without experiments, without result, then it's very difficult to comment.
Yeah, so it is mainly about the chemistry and the temperature. So
yes,
we can control temperature and the chemistry by adding some interlayer as well, maybe.
Yeah, see, if we add the interlayer, that is a different solution, right? So interlayer, if we add a copper interlayer or say zinc interlayer, that is a different solution. But it also hampers the property. So what we are asking, say, our joint property, that is interlayer property will come. But what we are suggesting, without adding any interlayer, can it control the intermetallics or IMC or preferred intermetallics, so that we get the desired property? If you play with the parameter, not the say adding some other things. If we had other things, guys, there will be say solution already available, right?
Yeah, definitely. Yeah. I think we have all the questions from this meeting, and thank you very much again for the excellent presentation. And I will share the link of the recording. So if people want to recap, you can look through that again. I will share the link after the meeting.
Okay, sure, definitely.
Yeah, I think here we are almost towards the end of the meeting, and yes, thank you very much. And
thank you Tierju, and thank you other participants, especially Derek and the other people. So thank you for the invitation, and thank you all for listening.
Yeah, hope we can have some future collaboration, and we'll keep in touch with you. Yeah, thank you so much.
Yeah, definitely. I am waiting for this proposal to accept, and so that I quickly go to WMG to meet you guys.
Okay, so I hope I can see you in Warwick. Yeah.
Okay. Thank you.
Okay. Yeah. Thank you very much.
Thanks a lot. Thank you very much.